But we're moving to chapter 6 finally, and this is really going to look like the chemistry that we've been waiting for, with chemical symbols and formulas and stuff. So everybody probably knows, and if you don't, please don't feel bad, that water has often something called a formula. And when we say H2O, most of us know, oh, that's water. So how come? Well, every substance in the world, at least every substance that we know, has a composition that is constant, that doesn't change. And that composition is typically a combination of different elements, different kinds of atoms. In the case of water, water is always composed of these two ingredients in those proportions. Meaning 1 unit of water, 1 molecule of water has 2 hydrogens, that's what that 2 means. And there's a 1 here that we don't write, is implicit, there's 1 oxygen. So going forward, today we're going to talk about formulas of 2 kinds of compounds. There's many kinds of compounds, but we can classify them generally into 2 big groups, something called ionic and something called molecular. So ionic versus molecular is what we're going to talk about in chapter 6. So chapter 6, ionic and molecular compounds. And the word compound means composed of more than 1 different thing. Now, water happens to be a molecular compound, not an ionic compound. So what we're going to take a look today is how we distinguish the 2 and how the different ingredients, the different atoms, are joined together in the 2 different kinds of compounds, in ionic and molecular. And we're going to start with ionic. Now, this not being ionic, I need to give you an example of an ionic one. Sodium chloride. And we're going to learn how to name them too. So I just threw out the name sodium chloride and then I put a formula. Well, by the end of today, you're going to know how to come up with the formula for ionic compounds, how to come up with the formula for some molecular compounds, not every molecular compound. There's many more molecular compounds than ionic. And also, you're going to be able to name molecular compounds and ionic compounds when you look at the formula. So you're going to go both ways. Write the formula, name the compound. Now, in chapter 5, we learned that all elements on the periodic table, except for the elements in group 18, are somewhat unhappy. They're not happy the way they were created, the way they are found in nature. So they're always looking for that happiness. And we define in chapter 5 something called the octet rule. And I'm going to put in parentheses an exception called the duet rule. The octet rule tells you that all atoms in the periodic table want to have 8 electrons in the outermost shell, in the outermost apartment, if you will, in the highest floor, because that's what makes them happy. 8 electrons is equal to happiness in the chemistry world. Now, for some elements, and there's only very few, 2 is the magic number. Now, 2 is the magic number for hydrogen and essentially only hydrogen.
Because it can only have 2.
because it can only have 2 electrons in the outermost shell. That first floor of the every atom, if you remember, has only the 1s apartment, and the s apartment, the s orbital, can only hold 2 electrons. So there's no more electrons that you can give hydrogen. So for hydrogen is 2. For every other element is 8. Now, in an effort to complete an octet, to have 8 electrons, we mentioned in chapter 5 that some elements give off electrons, some elements pick up electrons. So depending on where they are on the periodic table, they may actually do one thing or the other. So let's take a look at one periodic table again and see if we can predict some sort of a pattern to help us with the location, to help us with the loss or gain of electrons. And then there's something super important that we also learn in chapter 5, that when an element either gives away or picks up electrons, they're no longer neutral. They're going to carry an electrical charge. They're going to be ions. So very quickly, looking at the periodic table, you can see, once again, the group numbers on the top. We're going to concentrate on groups 1, 2, 13, 14, 15, 16, and 17. We will talk about some elements in this shorter part of the table. But the predictions that we want to make right now is the following. Can we say with a certain degree of certainty whether any of these elements are going to be losing, gaining, or doing something else with electrons? And the answer is yes, we can. We can be certain that elements in this area are always going to be losing electrons. These are called metals. Now, all metals are going to have a tendency to lose electrons. They're going to prefer to do that. There are a few metals over here too, and I'm going to just highlight them. It sort of goes like this. So these guys are also metals. They behave like metals. And all of these guys also behave like metals. So one rule to remember is that metals tend to lose electrons. Okay? That is a rule that you had to remember. Now, what about these guys over here? We're not going to consider these at all because these are non-reactive. They are not going to lose, gain, or do anything else with electrons. They're happy with their 8 electrons that they already have. But these guys are considered non-metals. And we're going to have to deal with them. As a general rule, non-metals have a tendency to gain electrons. That's, in general, what happens. Now, that's fine. We can make that prediction right away and be confident that our prediction is going to be correct 99.99% of the time. In fact, all the time in this course. So metals on group 1 for this course are always going to lose 1 electron. So the group number tells you how many electrons are going to be lost. So these are going to be losing 1 electron. 1 electron gone, if you will. Elements in group 2 are going to have a tendency to lose 2 electrons. So my up arrow is like losing. Okay, now, if you forget, then just remember the group number tells you how many electrons metals are going to lose. So metals lose electrons. That you have to remember. So what is the prediction? Elements, let me start with this. Elements in group 17 need only 1 electron to complete an octet. Remember that the 7 tells you that they have 7 electrons on the outermost shell, on the highest floor. That's what we said last week. So they need only 1 to complete 8. So these guys are going to have a tendency to gain 1 electron. I should probably put gain. 7 plus 1, 8 electrons. So if you look at the group number, whatever is away from 8 is how many electrons these guys are going to tend to gain. So group 16, 6 electrons in the outermost shell, is going to look for 2 electrons, so they're going to have a tendency to gain 2 electrons. Gain 2 electrons. And then finally, nitrogen and phosphorus are going to have a desire to gain 3 electrons. Okay? So we have now set certain parameters that we have metals always lose electrons, non-metals sometimes lose electrons, not always. We haven't even talked about carbon, which is super important, but we'll talk about it later. And the number of electrons either gained or lost can be predicted by the group number where the element is found. Now, we're going to leave the other scenario because there's a second scenario. This one, elements lose or gain electrons. The second scenario is when they do neither of those two things, they do something different called sharing electrons. So the sharing of electrons comes on the second part of this discussion. Right now we're going to concentrate on the gaining or losing. Now, here is an important thing to remember also. So I'm going to erase this, erase that. Let's erase water for now, and I'm going to put NaCl up here. The chapter deals with ionic and molecular compounds. So let's distinguish right away what is an ionic compound. So an ionic compound is super easy to figure out. It always has a metal combined with a non-metal. It's a partnership between metals and non-metals. Between metals and non-metals, ionic compound. Molecular compounds only non-metals. In other words, there cannot be a metal on a molecular compound.
But it's two non-metals?
Only non-metals. Partnership between only non-metals, 2 or more. You can have same thing here, 2 or more. Okay? Partnership between 2 or more metal and non-metal, or only metals. Does that make sense?
Yep.
Okay. Now, predicting then whether or not a chemical is ionic or a chemical is molecular is just a matter then of looking at the partners, what's on the chemical. With one important exception. this guy right here, hydrogen, is really an ambiguous type of element. This element sometimes behaves like a metal, sometimes behaves like a non-metal. So compounds that contain hydrogen are going to be both ionic or molecular. Not both at the same time, but they can be one or the other. And now we're going to take a look at some examples of metals becoming ions and some examples of nonmetals becoming ions. So what is an ion? We sort of introduced the idea of ions at the beginning, during the last chapter, but we never really formally defined what is an ion. So now we're going to have to make a more formal definition of what ions are. That they are elements that have lost or gained electrons. So that's a more direct definition. Now, as you can imagine, you can have positive ions and you can have negative ions. So a positive ion is going to be an element with a loss of electrons, which are going to be metals. So metals are going to form positive ions, ions that have a positive charge. Let's do some examples here. If you look at your periodic table and you look at group 1, let's ignore lithium for now, because although we can predict what lithium does, let's skip to sodium. I believe right below lithium, we have sodium. So sodium starts with 11 protons and 11 electrons. That's from the periodic table, right? When sodium loses an electron, so one electron goes away, sodium becomes Na1+. It still has 11 protons, but this electron that went away is now subtracted from the total of electrons. So it has 10 electrons. Does that make sense? Yeah. So you start with 11 electrons, you lose one electron, you have now 10 electrons, 11 protons. Protons are positively charged. You have a surplus of pluses. The charge of the sodium atom is now 1+, and this is called a sodium ion. The same thing is going to happen to potassium, which is right below sodium, to rubidium, Rb, and to cesium, Cs. We don't have to worry too much about cesium and rubidium. Potassium we will encounter a little bit more. Now let's go to the second group on the periodic table. So I'm going to skip beryllium and go straight to magnesium. So now we have magnesium, which is found in group 2. Magnesium is going to have a tendency to lose 2 electrons because it's in group 2. And in doing so, it's going to become an ion of magnesium. Let's look at the charges. So magnesium has what atomic number? 12. So 12 protons, 12 electrons. It's going to lose 2 electrons. So it's going to remain with 12 protons, but now it's going to have 10 electrons. And the charge of this ion is to be indicated as a superscript as 2 plus. Sometimes you see them as plus 2 instead of the sign being at the end is at the beginning. Same thing. But the point is that you have now an ion with a charge. The same is going to happen to calcium, which is right below magnesium, to strontium, which is Sr and is below calcium, to barium, and that's where we're going to stop. We're not going to look at Ra. Now, one more positive ion, and then we move on to the negative ions. And that is found in group 13, and is aluminum. It's probably the only one that we're going to take a look on group 13, although we could say that gallium behaves the same way. But let's take a look at aluminum. Aluminum is going to have a tendency to lose 3 electrons because it's in group 13. And what is the atomic number of aluminum?
13.
Okay, so we're going in order. 13 protons, 13 electrons. It loses 3 electrons, so still 13 protons, now 10 electrons, and a charge of 3 plus. And that is the prediction. Let's see if it opens, yeah. Okay. These are the metals. These are how metals lose electrons and become positively charged. Now, there's a name for positively charged ions, and that name is cations. Positive ions are called cations. And now let's switch to negative ions, which are going to be the result of elements gaining electrons. That's the prediction. May I erase this? Is it okay if I erase it? So now we're going to go to negative ions. Element with a gain of electrons. The name of the negative ion is actually an anion. An ion. Okay, so let's take a look at chlorine. Chlorine, atomic number 17, so it has 17 protons, 17 electrons. Chlorine is going to have a tendency to pick up an electron. So an electron is going to come in. So it's going to combine with this, and it's going to form an ion with a charge of -1. Why is that? Well, as you can imagine, it's because the number of protons doesn't change, but this one goes up to 18. So chlorine now has 18 electrons. Now here comes a little bit of a, not a curve, but something that you had to try to remember. When we were dealing with the positive ions, sodium became sodium ion, magnesium became magnesium ion. In the case of the negative ions, chlorine becomes not chlorine ion, but chloride. So there's a difference. We could call chlorine chlorine ion. I mean, I could simply say this is the chlorine ion.
But does that imply a positive charge?
I guess so. I never thought about it. What is the implication? But the implication is that if you don't change the name, you would have to add the word negative, chlorine ion negative. Sorry, if you put the ending IDE, then you don't have to state the charge. Does that make sense? So chlorine ion is going to be renamed chloride with that IDE ending. So this is chlorine, this is chloride. For the positive ones, we just have to live with the fact that we call them ions. Sodium, sodium ion. Magnesium, magnesium ion. Okay, so that was group 17. Let's take a look at what happens with a member of group 16. And I'm going to pick sulfur just because it's right next to chlorine. So S for sulfur is going to have a tendency to pick up 2 electrons. 2 electrons are going to come in. Sulfur starts with 16 protons and 16 electrons. When it picks 2 electrons, it's going to become sulfur 2 minus. And it's still going to have 16 protons, but it's going to have 18 electrons. And we're going to call it not sulfur ion, but sulfide. Sulfide. Chloride, sulfide. Now, if we were oxygen, by the way, it would be oxide, like in carbon monoxide or carbon dioxide. So we'll get there soon. Now, one more thing that I want to say about this is that this number of electrons after they have gained 1 or 2 electrons gives them an octet, remember. And they look like members of group 18. Not because this is 18, but because the noble gas in front of them is going to have 18 total electrons. So they are going to become what we call in chapter 5 isoelectronic with elements on group 18. So let's do one more and then we can start combining them. And for that, I'm going to go to phosphorus, which is right to the left of sulfur. So we have finally phosphorus, group 15. So 5 is 3 away from 8. So phosphorus is going to have a tendency to gain 3 electrons. Phosphorus starts with 15 protons and 15 electrons. When it gains 3 electrons, it becomes phosphide. And it's going to have still 15 protons, but it's going to have 18 electrons. A charge of 3 minus. This looks very, very, very busy. When we start writing ions without putting electrons and protons, it's going to be a lot more clear. And you're going to be able to do that almost without thinking when you practice enough. So phosphide. Okay, so that's the end of the predictions to learn the basic rules of ion formation from metals and from nonmetals. Metals are going to form cations. Non-metals are going to form anions. Metals are going to have positive charges. Non-metals are going to have negative charges. Now let's try to make predictions as to what happens when they combine. Where are these electrons going? Where are they coming from? Well, let's take a look. Starting with sodium as the example. Sodium has a charge of 1 plus, right? We said that earlier. If we combine that, so this is plus, meaning a combination, with chloride as an ion, you already know where the electrons went or came from. What we end up with is the following. We end up with something that has that chemical formula, but the question right now is, how do I know that that's the formula? Well, first of all, whenever you write a formula of an ionic compound, you always put the metal first. always the metal first, and then the non-metal second. In other words, I could not write it like this. That would be unacceptable. Nothing wrong with it because it really tells you the proportions. But the convention, the practice, tells you that you put the metal first and non-metal second. Okay, now, how do I know that exactly one of these is going to combine with one of that to give me this formula? I'm going to put a number here and a number there because that's what they imply. Remember, in formulas, I have mentioned in the past that when you have one atom of a certain element, we don't write the 1. Now, where did this come from? They came from these charges. So 1 plus gets neutralized or canceled out with 1 minus. So essentially what we did is we said, okay, the charge of the ion I'm going to put as a subscript on the chlorine, and the charge of the chloride ion I'm going to put as a subscript in front of the sodium. I crisscrossed charges. Well, this seems complicated for such a simple molecule, right? For such a simple compound. But that's what we did. Now, because they are ones, we don't need to write them. So we're going to erase them. So here comes a question. Okay, how is this useful? Well, what happens if I combine magnesium instead of sodium with chlorine? So these are still ions because we are dealing with ions. So 2 plus, 1 minus. Now the crisscrossing becomes useful.
So you have 2 chlorine?
Correct. So let's see what happens when we predict the formula. What is going to be the formula when these two guys form a partnership? Well, you have to start with the fact that you have to write the metal first and the non-metal second. So the formula is going to be some variation of MgCl. But the problem is that unlike sodium and chlorine, you don't have one of each here. Why is that? Because ionic compounds need to be neutral after the partnership is established. In other words, the number of pluses and the number of negatives in the whole formula has to equal 0. Plus charges and negative charges need to cancel each other out. Let's make the crisscrossing thing that we did before. So I'm going to move these 2 plus, and I'm going to put it in the formula as a subscript of chlorine, and the 1 minus, I'm going to put it as a subscript of magnesium without the signs. The signs are never shown in formulas. So if that 2 moves here, that means that I have to put a 2 here. If this 1 moves here, that means that I have to put a 1 here. But 1s are implied, so I'm going to erase it. This one I'm going to get rid of. And now check this out, just for a second so that you see the charges. This guy has a charge of +2. This guy has a charge of -1. If I am saying that essentially what this represents is the following: a magnesium here with 2 chlorines around it. One chlorine combining with magnesium. That's what I'm indicating here. Okay? How is this neutral? Well, 2 times -1 is -2. 2 times 1 is +2. +2 plus -2 gives you 0. The easiest way to predict the formula then is just simply to crisscross rather than putting these numbers over there. And that was just as a reference. I'm going to erase them. Let me give you one more example, and then you're going to make the prediction yourselves. So let's put here a combination of aluminum ions, and let's make it easy with chlorine. Aluminum is in group 13, so we're going to predict that this guy has a charge of 3 plus. Chlorine is still the same chlorine, so it's going to be 1 minus. What is going to be the formula of that combination? Well, if I crisscross to predict the subscripts, so these are subscripts, I'm going to end up with a formula with the metal first, the non-metal second, and the crisscrossing tells me that I have 1 here and 3 here. And that's in fact the correct formula for that compound. Now, before I challenge you to predict one, let's name them. And it's really easy. You simply name them by mentioning the metal first, without the word ion. I know that this is a sodium ion, but I'm just going to say sodium instead of sodium ion. And then the name of the second ion with the ending IDE. So sodium chloride, chloride, chloride. The number here doesn't matter. We're going to combine magnesium with oxygen. So we're going to put magnesium here, and we're going to combine it with oxygen. Before predicting the formula, let's put the charges. Magnesium group 2, 2 plus. Oxygen, 2 minus, because it's in group 16, so it needs 2 electrons, so it's going to be 2 minus. So if we crisscross, let's make the prediction. What's going to be? First magnesium, then oxygen. So 2 and 2, right? So we're going to put a 2 here and a 2 there. That will give you a 0, okay? And the name of the compound is going to be magnesium oxide. The only problem is that chemists like simple things. Whenever possible, they like simple things. If these two numbers are the same, they can be simplified to a 1. In other words, you divide the 2 by each other. 2 divided by 2, 1, 2 divided by 2, 1. So this is not really the right formula. The right formula is simply that. MgO, 1 of each. Because in reality what you have is 1 magnesium ion surrounded by 1 oxide ion. So they're floating around, attracting each other because positive attracts negative, negative attracts positive. So that's what we have. Let's have a little bit more fun with crisscrossing. Now we're going to combine aluminum with oxygen. Okay, let's predict the charges. What are the charges of those two ions? 3 plus for aluminum because it's in group 13. And oxygen, same thing as before, 2 minus. When we crisscross, what do we get? What's the formula for aluminum oxide, which you know how to name now? Al, what did you say? 2O3. And that is indeed the formula of aluminum oxide. How do I know it's correct? Because aluminum 2 times plus 3 is plus 6. Oxygen 3 times negative 2 is negative 6. Negative 6 and positive 6 cancel each other out. So this has a charge of 0. And it's called aluminum oxide indeed. Okay, let's make one more prediction. And then we can take a look at what Rachel actually asked. So let me pick a member of group 2, and a net member of group 17. What about calcium combining with fluorine? We haven't looked at either of those two yet, but you're going to make the prediction based on where they are on the periodic table. So calcium is in group 2. So what's going to be the charge? 2 plus. And it is a cation. Fluorine is in group 17. So what's going to be the charge? 1 minus. So the formula, putting the metal first, is CaF, and now crisscross. The 2 becomes the subscript of the F. Ca1, if you write it down, is fine. Just erase it after.
I put it with the pencil.
Okay, good. Yeah, I can put it right here and then make sure that I erase it. So Ca1, F2, and that gives you the charge of 0 because calcium is 2 plus, so 2 plus times 1 is 2 plus. Fluorine becomes fluoride and is a negative 1, so 2 times negative 1 is negative 2, so negative 2 plus positive 2, 0. What would be the name then? Calcium fluoride. So iron, Fe, is in the periodic table on group 8. There's no way for us to predict the ionic charge of that. We need to look it up. So if we look up iron in the periodic table, we find out that iron can actually form 2 ions. So let me show you. And that's easy to find by Googling things. You just simply use a search engine. I say Google. I could say, what is it, DuckDuckGo or something like that. There's a bunch of different search engines. Just Google happens to be the monopoly. But in the periodic table that I have, I clicked on iron just to see a little bit more information about it. And right here, there's something called oxidation state. The oxidation state gives you the ions that this element can form. And it can form a +3 or a +2 ion. How do we know which one we have? Well, it depends on the formula. So you sort of work backwards. Okay? Let me show you other examples and then we start working with problems. So for instance, copper. Also found in the middle of the periodic table, if I click on Cu, it brings the oxidation states of copper as +2 and +1. So unlike iron, which was +3 and +2, this one is +2, +1. Let's take a look at another metal, not very sure of itself. Manganese. Oh man. Manganese can have +7, +4, +3, +2. That's a lot of insecurity, isn't it? But that's what it is. Okay. Chromium. One more and then we start playing with them. Where is chromium? There. Number 24. Chromium can be +6, +3, +2. Now, let's stay with copper and with iron, because those are going to give us a new rule for naming that we haven't looked at. Okay? So here we go. The prediction of the formula is not going to be that difficult if I give you the ions. Okay? So I'm going to tell you, okay, tell me what is the oxygen product of iron with a charge of +3 when it combines with oxygen, which is always -2. And I'm sorry for flipping the +3, the 3+. It's just, I do it on purpose so that you get used to the fact that it doesn't matter where it is. You just look at the sign, whether it's before or after, it doesn't matter. So what would you predict is the formula of that? Fe2O3. Indeed. That's the formula. Perfect. Now let's put Fe plus 2 with oxygen. What do you predict is the formula? FeO. Very good. If I put Fe2O2, there's nothing wrong with that except that chemists want to simplify it. So we need to erase the 2's and leave the ones implied. Here comes the problem. How do we name them? I mean, if there was only this one, I would say iron oxide, right? As simple as that. So I would write iron oxide. And then I will come to this one and say, wait a minute, that's also iron oxide. Iron oxide. Well, that's not possible. These are completely different chemicals. They have completely different properties. They behave differently. You look at the charge of the iron, and you put it in front of the iron with a Roman numeral. Okay? And that distinguishes between the two. So,
Talk about the name. Let's talk about what name that you would call it.
right. So these are, we agree that these are both iron oxides, right?
Yeah, that's what, yeah. So the one
How do we distinguish them? You suggested you look at the number of oxygens. That's a great suggestion. As a Roman numeral. And that leaves no ambiguity. Iron 3 oxide. You just read it, you read the 3 as 3.
It's always the positive charge.
And it follows the positive ion, yes. Because you're naming the charge of the positive ion with a Roman numeral. Let's make a prediction for a couple of copper compounds. I'm going to give you the charges of both ions, and then you're going to make the prediction. And let's stay with oxygen, just because it's easy. So we have copper 1 plus and copper plus 2 plus oxygen. So let's make the predictions of the formulas. Crisscrossing gives us what? For the top one. Cu2O, yes, I like that. And then this one?
C-O-O. Also U-O.
And that's it. Now, they used to be called cupric and cuprose. No more. We're just going to say this. We're going to use this rule. So name of the ion, copper. So we're going to put copper. The charge of the ion, plus 1, parentheses, Roman numeral 1. And then oxide. Copper 1 oxide. That's how we read it. We don't say copper Roman numeral 1 oxide. We just say copper 1 oxide. Why not Arabic, the regular one? I have no idea, but the chemists are the ones giving us the rules, and we're going to follow them. So, copper, charge 2, oxide. All right? Now, here comes the challenge. Now I'm going to give you a name, and you're going to write a formula. So we're going to work backwards. Okay? In fact, let's do it over here. So now the game is, given the name of a compound, come up with the formula of the compound. Ionic compound that you need to name just by looking at the symbols. Potassium. So always name the metal ion first, and then bromine becomes what? Bromide. That's it. Not too bad, right? What is the formula for calcium iodide? Boy, I messed up on that one. So what do you think the formula for calcium iodide would be? Yeah, this is not as straightforward as before. We're working in reverse. CAI. Okay, but we'll get there. What's the charge of calcium on the periodic table because of the group number?
2 plus.
So 2 plus. And the iodide is in group 17 minus 1. So now just crisscross. So what's the formula? Ca1. That's it. Calcium iodide is CaI2. You're done. Let's do one more. So I'm going to give you aluminum fluoride. I don't think we did that one. So what's the formula for aluminum fluoride?
So it will be AlF3.
I love it. That's it. That's exactly right. AlF3, aluminum fluoride. Now for the last one, let me take a look because I need a different. Let's see. Oh no, that's only one. What about this other one? Okay. Let's see if we can name this one. I don't even know. Come up with a formula. Gold 3 oxide. Gold 3 oxide. So we need to find gold. What do you think?
I say that it's AU2O3.
AU2O3. So let me just, in my head, -2, +3. Yep, I agree with that.
My question, well, now that I press on the gold, I know the oxidation state is
+3 and +1, right, which is fine.
That's what I was trying to figure out.
Which is fine. Well, I gave you the oxidation state right here.
I still clicked on it too. I don't know
Yeah.
why.
So
We're not used to it.
this right here is the oxidation state. You just discover that. These guys don't have it because there's only one oxidation state. All right, now we're almost done with these ionic compounds. So now we're going to talk about something called polyatomic ions. So poly means many, okay, in whatever, Greek or Latin. So these are going to be ions with more than one atom, 2 or more. It turns out that there are some associations that don't look ionic, that they're actually more molecular, but that form these charged ions known as polyatomic ions. In this slide, there's 2 examples. One is called sulfate, and one is called nitrate. And you see the formulas. Don't be intimidated by that. We're going to work them through, and it's really, really straightforward. So let's take a look at some examples. These guys are all negative except for one, which is positive. So in other words, all of them are anions, with the exception of this one, which is called a cation. The charge is +1 on the whole thing. I'm not sure that I like the way it's written here, because it almost looks like it's on top of the 4. So what I would suggest is that when you look at the charge of a polyatomic ion, you can put it on top of it if you want to. Now, another way of doing it is just to put a parenthesis indicating that that whole thing is charged with a +1. Nitrate, the whole thing, the N and the O with the 3 oxygens, is a -1. Carbonate, the C with the O and the 3 is all together CO3, 2-. Put a parenthesis and maybe makes it a little bit easier. So how do we use them? Well, first of all, you don't have to memorize them. You always look them up. You can have a table. In fact, I'm going to put a table in that folder where the lecture notes are found. And you don't have to memorize this naming. So we don't need to know that nitrate versus nitrite is NO3, NO2. We're just going to look them up. So here's a table with a bunch of them. Okay? The PowerPoint has a nice summary of the whole thing that we've been talking about. If you're a visual learner and you like this type of diagrams, this may help you. I think we covered it in detail with examples, taking our time to make sure that we understand how this works. So I'm confident that once we open the homework in a few minutes, you're going to be able to work through this without any problem. The number of protons and electrons, both. Okay. Okay, so atomic number of nitrogen is 7. So then is a 7, a comma. You gain 3 electrons, so 7 plus 3, 10. I agree with that. Okay? Okay. Potassium, I think I'm going to skip that one. It's too easy. That one is also too easy. What about this one? That one is a little bit more complicated because, of course, it's a transition element. So let's look for iron. How many protons? What is the atomic number? 26? Okay. And this guy actually lost 2 electrons. So how many electrons are there going to be there? 24. So you need to know the arithmetic, and we're going to submit it, and you got it right. Okay, next problem. Okay, so here we go with the crisscrossing. The formulas are given to you. You don't have to write them. Writing them can be a challenge too, so we'll get to that soon. Ca3N2. I like that. If you have something else on yours, please. Now this one is superscripts, you see? So the reason why this would be wrong is because they're not as subscripts on the bottom. They're on the top. So that's the way we write them. Nothing wrong with the other one, by the way, but you know what? Chemists decided to use them as subscripts, not superscripts. Okay, what is the correct name for that? You may have a different one on your homework.
Just barium chloride. I don't think
Right.
it doesn't have nothing.
Correct. So this one probably does not have more than one oxidation state, so it must be barium chloride. This is sort of giving you a preview of what happens next with covalent, with molecular. Let's keep moving. Okay, so remember the rule. If there's a metal, ionic.
Lithium is a metal.
Right?
Let me see what else. Cesium is a metal. Potassium.
Now, here, oh boy, I'm glad we're seeing this thing because I was going to jump the gun and say, oh yeah, metal, ionic. However, to have an ionic compound, you had to have a negative ion too. In other words, you cannot have two positive ions in ionic compounds. My suggestion was, if you look at a formula, and the formula is correct, if you see a metal, ionic. But here is a trick question, because of course, both silicon and phosphorus are nonmetals, so that's not going to be an answer, right? Lithium metal, okay, maybe. Iodine nonmetal, so yes, that's going to be an answer. This is the trick one. Zinc is a metal, so I'm going to say yes. Magnesium is also a metal, yes, but not together. Together they cannot combine to form an ionic compound. You need a positive ion and a negative ion, not two positives, not two metals. You need a metal and a nonmetal. It was on the definition still here, metal and nonmetal. So that's not going to be an answer. Sodium and neon. Neon is a trick question. Neon is not a metal and it's not a nonmetal either. It's on group 18. Remember, the nonmetals end right here. This way. These guys are not considered nonmetals. They are a group on their own. They're an exclusive club. They don't mingle with anyone. The noble gases.
So those are the ones that the other ones are striving to be like.
Exactly. All of these guys want to be like them. These are the billionaires, the elites. You got it. These are the elites. Okay. Remember, capital B, lowercase a. Template. That one. And what do I put?
3.
Yes, I agree. Click outside of that. And the template again. And now what? 2. And submit. All right, so let's go to the next question.
It's the same.
Same type of, okay. So more practice, okay. But we're getting good at this. I mean, my goodness. This is a lot of stuff that you are able to do after one single chapter. So we have Al2O3 and we're supposed to name that. Remember, if the ions are single oxidation state, we're not going to struggle. We're just going to call them by the name of the metal ion first, and then the name of the negative ion with the IDE ending. So what would that be? Al2O3 in my screen.
Sorry, I wasn't even paying attention to that.
What was that?
Aluminum
You got it.
oxide.
Aluminum oxide. And they just want the spelling. You know, I'm going to put it all in lowercase and see if it doesn't tell me that I need to use, you know, first letter capital. One quick thing here. I'm going to spell this like that. Aluminium. That's the British spelling, by the way. It does exist. I'm curious to see what it does.
And you put a space after the aluminum oxide?
Yes,
Okay.
yes, which is actually also a very good point. Let me put them together. So I have potentially two mistakes here. Ah! And he left it like that, as aluminium.
But I wrote my fluoride thing and they put it wrong. And then I put them caps and they change it for
Lowercase?
lowercase.
Okay, let's do the capital.
Be wrong in the first
Calcium chloride with capitals. Let's see. Ah, he changed it to lowercase, but it gave him correct. Okay. Okay, all of these are single single oxidation states. So I'm gonna skip to see if we get to one with Roman numerals. Okay, same thing. This is just more of the same. 13?
Oh, this one has it, the 13.
Oh, perfect. Okay. So iron 3 chloride, express your answer as a chemical formula. So, what do you think? Do you have a different one than that one?
I did.
Yeah, I have cobalt and fluoride.
So do
Okay.
I have cobalt 3 and fluoride.
Okay, so what would you write for cobalt 3 and fluoride?
Let me find cobalt. CO.
CO.
What I put CO.
But it's 3. No.
Probably the chloride is the one with the 3, the fluoride.
That's what I was thinking. So COF3.
Sounds good to me. FeCl3. Yeah, so this one you had to do a two-step in your brain because the 3 is not the subscript, it's the subscript of the other one. You may be in better shape if you have a piece of paper and you just, yeah,
I do that a lot.
What did you
good.
do? Because they said mine was wrong.
Oh, I did right here. The 3 goes to the other side.
Yeah.
Did you put it under or
I
did you put it
know.
on top?
I see what I did wrong. It was one of the letters. Yeah.
Okay.
you're right. Okay.
So lead 4 oxide.
Oh, I have that one.
Okay, let's do this one then.
I'm gonna write it on my paper just in case.
Okay. So lead 4 oxide, lead is Pb.
PB.
Now, I had to put this on the board here because Pb and then oxygen. I know Pb, I'm being told it has a charge of 4 plus. So 4 plus. And oxygen is always 2 negative. So it's going to be, oh, this is an interesting one. Can you see that from where you're sitting? See, this is an interesting one. So, crisscross, 4 and 2, right? But now, That's
212.
one,
PB02.
exactly. That's one with a subscript that has a common denominator, meaning you can simplify it by dividing both numbers by 2. So 2 divided by 2 is 1. We're going to write PB with an implied 1. 4 divided by 2 is 2. So that is preferred over this. Nothing wrong with the proportions on the first one, but it can be simplified. So let's see. PBO subscript 2. Okay. You know, mercury, which I haven't seen yet, is a tricky one. If you run into one with mercury and you get it wrong, please do let me know next week. I don't see anyone with mercury, but the ions are weird. In fact, let me see if I can show you here just very quickly. Hg. Where are you, mercury?
Mercury is in the 12.
Oh, there. Thank you. No, it doesn't show anything here. Okay. Let's go back to the homework. And what is this one?
15 is the same.
Same, okay, so let's go to 15. Okay, so now these are polyatomic ions. And we haven't done enough work with those, so let's practice a little bit.
Okay.
Select the correct name for K3PO4. So remember that we name compounds always with the positive metal first, positive ion, followed by the name of the negative ion. That doesn't change with polyatomic ions. So what do we have? K, potassium. And then we have PO4. So we look at this table for PO4. Excuse me. Let's see where's, oh, there it is. Right there. And the name of that ion is phosphate. So we're just going to say potassium phosphate. And that's it. No more. And that's one of the choices.
Oh, what did I do?
Okay. So that was number 15. Did you guys get a different one other than K3PO4?
No, I got the
Same one? Did you get the same one?
Where?
For problem, we are on 15?
On 15.
Yeah. Which, just curious to see if you get the same one.
The next one is backwards.
And it's phosphate instead of phosphate.
Okay, let's take a look.
Yeah, this is the same thing.
It is the same thing, okay. Let's move on then to 16, which I think is in reverse, you said?
Yeah.
Okay, so what is the formula for potassium phosphate? So we write the first one is potassium, so okay. And then the phosphate, let's find it on the table. PO3. Now, I'm going to put the PO3 here. However, you guys, phosphate has a charge of 3 minus. Potassium has a charge of 1 plus. So when we crisscross, we end up with K3PO3. Now, we don't need a parenthesis here because this doesn't have a subscript, doesn't have a number. The number is 1 of these. If I had 2 of these, then I would have to use a parenthesis. So what are the choices? K3PO3, KPO3, etc., etc. K3PO3 looks like this.
The first one.
The first one.
So the number on the side of the O, that always stays there, that doesn't change?
Right.
Okay. And you're just doing the chart, the other charges?
Correct.
Okay.
Correct.
That's why I put it here.
Okay, so let's mark that one. And number 17. These are polyatomic ions. Write the formula including the charge for each of the following polyatomic ions. So for that we need to go back to the table in the previous problem. Hydrogen carbonate or bicarbonate, okay? Either you Google it or you go back to the previous problem, bicarbonate. Bicarbonate, I don't see it there. Hydrogen carbonate, right there. So hydrogen carbonate or bicarbonate. HCO3, -1 or -1. They don't like the ones, so we're just going to put the HCO3 with a negative sign. So HCO subscript 3, and then, oops, I guess I can put that. Oh, what is this? Yeah, but it created, hold on.
Oh, yes.
3 negative, just like that. Is that what you guys are doing?
Yes.
Mid. Okay. You want me to help you with the one you have?
Perchlorate, whatever it is.
Perchlorate or perchlorate? They're both exist. Perchlorate. Okay. So let's go back to the previous problem. So where is perchlorate? ClO4 with a -1. Just minus, like that. Don't put the 1 because I guess it doesn't like it. You can always either take a screenshot of this table or find a table in the internet with polyatomic ions.
That's what I'm gonna do, take a picture of it. And then when we do the home study.
Okay, I'm going to go to 18 now. It's still in polyatomic and it's the same, so I'm going to skip that one. Wait a minute.
Express you as an ion.
Yeah, they're still ions. Okay. Yeah, let me just, I'm trying to find a different type of question. Now we have one here in which we may need to use parentheses. So let me go to one with parentheses. Enter the formula for the polyatomic ion of, okay. So they basically want you to work backwards and realize that the CO3 has a charge of 2-. That's all they're trying to ask you in this problem. So let me see if there's something a little bit more instructive than that.
There's some that already
Ah.
have parentheses.
Okay. I want to write one with parentheses. Excuse me. Yeah, so all of these are already, yeah, I'm going to skip that question, you guys. I think you can, all right, so we're done. Okay, so now we have one last thing to discuss before we cover this entire chapter, and that is molecular compounds. So when you do not have a metal, you're going to form what are known as molecular compounds. So molecular compounds are always two or more nonmetals. There's no metal. Let me give you an example from something that you've seen before. CO2. I'm choosing not to use water because water has hydrogen, and hydrogen is a pain. So I don't want to confuse you because you're going to look at hydrogen in the periodic table and think it's a metal. Let's go with that. Two nonmetals for sure. Carbon is a nonmetal. Oxygen is a nonmetal, right? So two nonmetals form what are known as molecular compounds. In this case, you don't form ions. Atoms in molecular compounds do something else. They share electrons. But they share electrons with the same goal that metals and nonmetals had when they form ionic compounds, and that is to complete an octet. But they're going to complete an octet not by taking electrons or giving electrons, but by sharing them with another atom. So let's see how that happens. Say that again?
Covalent bond?
Covalent bond, correct. So the name of the bond between two non-metal atoms is indeed a covalent bond, just like you mentioned. But let's see how that gets formed. It's a little bit different. Give me about 5 more minutes. We have until what, 10:40? Okay, so 10 more minutes should do it. And I'm going to use carbon dioxide, although this is a difficult one, as an example. Remember in chapter 5 we learned something called the electron dot structure of atoms. That is where we put the electrons on the highest floor as single dots up to 8 around a single symbol. So carbon is in group 14. It has 4 electrons in the top floor, right? Group 14. So we're going to put 1, 2, 3, 4 electrons. Now oxygen is in group 16, right? Now according to this compound formula, we have 2 oxygens. So I'm going to put 2 oxygens here. First one right here. And just to make things a little bit more clear, the electrons are the electrons, but to make it more clear, I'm going to make the electrons of the oxygen little x's. 1, 2, 3, 4, 5, 6. Okay? Now, remember when we did this last week, we said, okay, so you put 1 dot on each of the 4 possible sides if you have 4. If you have 5, you can start pairing them. So you can put 2 here and 2 there. Or you can put 2 here and 2 here. In other words, this would be the same, right? But you should not do more than that. In other words, don't put 3, don't put 4. But here comes something interesting. Let's put another oxygen here. 6 little x's. 1, 2, 3, 4, 5, 6. Now, when carbon is near these 2 oxygens, the electrons of this atom fill the nucleus of this atom, but the electrons of this atom fill the nucleus of this atom. So they start attracting each other. When they attract each other, they realize, wow, we can actually establish a partnership so that I, carbon, feel like I have 8 electrons. Although they're not all 8 mine, I'm sharing them with another element. So this is what happens. I'm going to bring this oxygen in close proximity here, leaving these two on one side. So I'm going to put the oxygen here, and I'm going to put 2 electrons right there, and these 2 other electrons where they were. Now, what am I going to do with this electron? I'm going to move it to here, and this electron I'm going to keep there. So I'm going to put it right here. I still have 6, right? I mean, I just rearrange them. 1, 2, 3, 4, 5, 6. But this electron now is partnering with this electron. And what I'm going to do next is do the same with the other oxygen. So I'm going to put the other oxygen on the other side with the 6 electrons that I have here. 1, 2, 3, 4, 5, 6. I'm going to move this electron, just because I can, to here. I'm going to put it on this side. So now these guys sort of look similar. But importantly, now this electron is filling this electron. They're sort of partnering. This one doesn't have 1, but I can always move this guy from there, is still in the carbon, to here. Correct?
And you can move the top.
And then I can move the top one from there to here. Now, I did not add or remove electrons. I just rearranged them in space so that they would look in a way that I can count them as being members of all 3 atoms. So now, check this out. This oxygen fills its own 6 electrons, 2, 4, 6, plus these 2 from this carbon. So if we count, we have 2, 4, 6, 8 around the oxygen. Around on quotes. If we count for the carbon, we have 2, 4, 6, 8 around the carbon. If we count for the second oxygen, we have 2, 4, 6, 8. So each element has now 8 electrons, or at least they feel like they do. The last thing that I can do here, and that's the so-called covalent bond, is replace these dots and these X's with dashes. Let me put it over here because I don't want you to lose sight of that image. I'm going to put oxygen there, 2 electrons, 2 electrons. Instead of these 2 dots, or X and dot, I'm going to put a line. And then instead of that pair of electrons, and I'm going to put another line. And then I'm going to put the carbon. I'm going to repeat the same process over here. I have the oxygen, the 2 electrons, the 2 electrons. These 2 partners I'm going to draw as a line. These 2 partners I'm going to draw as a line. And now I have a new drawing showing exactly the same thing, except that pairs of electrons on this one are shown as dashes. This right here is called a covalent bond. I never mentioned this to you in the previous discussion, but the attraction between a positive ion and a negative ion is called an ionic bond. It's an attraction. So this dash represents 2 electrons being attracted both to 1 carbon and 1 oxygen at the same time in something called a sharing of electrons. So it's a sharing,
So would that mean that there,
1 pair of electrons. Yes, go ahead.
Does that mean that there's 4 covalent bonds in this?
Exactly. This whole molecule now has 4 covalent bonds. It turns out that every atom on the nonmetal world, I mean just like the metals, but in these particular nonmetals, they like to feel the presence of 8 electrons. Instead of having them, they just want to feel like they are in the neighborhood. So if you count, you have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8 for each element. That's a molecular compound. Now, this gives these partnerships a very nice stability, if you will. But the bulk of what remains of this chapter is just naming them, not writing them like this. This was an introduction to what comes next. And in fact, you do a lot of this in biochemistry and in organic chemistry. Very quickly, let me show you what happens with water. Hydrogen, hydrogen, oxygen. That's water, right? Hydrogen comes in with 1 electron only. It doesn't have more, right? Group 1, 1 electron only. Oxygen has 6, just as before. 1, 2, 3, 4, 5, 6. Now, if I bring these two guys closer together, this electron and this electron form a partnership. So I'm going to join them in a covalent bond. And now hydrogen feels like it has 2, a duet, not an octet, because hydrogen always looks for only 2 electrons. 1, 2. Oxygen, 1, 2, 3, 4, 5, 6, 7, needs 1 more, so it's going to join to that electron with a covalent bond. So now we have that, and that, and that's the water molecule. It gets a little bit more complicated than that because this is a better drawing. I'm going to show you the one that is preferred than this drawing. There's a reason for it. We'll explore that in the next chapter. Yes?
In biology, we had to do the molecule of water, so we had to use the root.
With the models, right. And they end up being at an angle, not in a straight line. There's a reason for that. These electrons are pushing these electrons as far away as possible. In 3 dimensions, that's called a tetrahedron, or a pyramid, if you will. Okay, how do we name them? You're going to use Greek prefixes. And the table of prefixes is right here. So if you have 1 atom, you're going to call them mono. If you have 2, di, 3, tri, etc. So in this case, the proper name would be, you have only 1 carbon, monocarbon. You have 2 oxygens, dioxide. We still keep the IDE ending for the second partner. Now, the reality is that when you have a single atom on the first member, we don't say monocarbon. We just simply assume that that's a single one. Okay. So carbon monoxide, carbon dioxide. Okay, now 10 seconds more. Let's see here. Bunch of examples. Carbon disulfide, 2 sulfurs, disulfide. Nitrogen oxide, why not monoxide? I disagree with that. I would say this is called nitrogen monoxide. That is improperly named because there's no reason why we should be calling carbon monoxide mono, but not in this one. So that should be nitrogen monoxide. Dinitrogen, 2 nitrogens, oxide. So we'll pick it up here just to wrap things up next week, but I think we're pretty much done with chapter 6.